In the profound, silent darkness between worlds, a colossal golden eye drifts. It is a machine of exquisite complexity, a marvel of human ingenuity, 100 times more powerful than its celebrated predecessor. Its gaze is fixed not on the familiar celestial neighbours of our solar system, but on the very edge of conceivable time, on the dawn of existence itself. This instrument, the James Webb Space Telescope, was not built merely to see farther. It was constructed to remember. It is a time machine fashioned from beryllium and gold, designed to capture the faint ancient light from the universe's infancy. For decades, our story of creation has been elegant, a cohesive narrative that begins with a single, infinitely dense point. A moment of unimaginable violence and incandescent potential we call the Big Bang. This theory has been the bedrock of modern cosmology for nearly a century, a grand epic of cosmic evolution that has, until now, stood firm. But the first dispatches from this new sentinel in the void are unsettling. The initial images relayed across 1 million miles of empty space are not what we expected. They are beautiful, certainly, but they are also deeply strange. They whisper of an era far more complex, far more mature than our models predicted. The data suggest that the very first chapters of our cosmic story may need to be rewritten. And in doing so, it forces us to confront a terrifying question. Did this magnificent observatory, in its quest to witness the universe's birth, inadvertently uncover evidence of what came before? Did James Webb just stumble upon the trigger? To grasp the magnitude of this potential revolution, we must first journey back. Not to the beginning of time, but to the beginning of our understanding of it. For most of human history, the cosmos was a place of serene permanence. The stars were fixed points of light in a celestial sphere, an eternal and unchanging backdrop to the chaotic drama of human affairs. This view, comforting in its stability, was shattered in the early 20th century. It began with the meticulous work of astronomers like Vesto Slipher, who noticed something peculiar about the light from distant nebulae. These fuzzy patches in the sky, later understood to be entire galaxies, were not static. Their light was stretched, shifted towards the red end of the spectrum. This phenomenon, known as redshift, was a cosmic fingerprint of motion. It was the celestial equivalent of a siren's wail changing pitch as it speeds away. Almost every galaxy he observed was receding from us at incredible speeds. The implications of this were staggering, but it was a Belgian priest and physicist, Georges Lemaitre, who first dared to follow the logic to its ultimate conclusion. If everything is flying apart now, he reasoned, then in the past, everything must have been closer together. If you were to rewind this grand cosmic film, the galaxies would rush back towards each other, the space between them shrinking, until everything in the observable universe, every star, every planet, every atom, was crushed into a single primeval atom. A day without a yesterday, a point of absolute beginning. This radical idea was met with considerable skepticism, even ridicule. The name Big Bang was coined not as a title of respect, but as a term of derision by the astronomer Fred Hoyle, a staunch advocate for a steady, eternal universe. Yet evidence for Lemaitre's cosmic genesis continued to accumulate. Edwin Hubble, using the then largest telescope in the world, confirmed Slipher's observations on a grander scale, establishing a clear relationship. The farther away a galaxy is, the faster it is moving away from us. The universe was undeniably expanding. The final, unassailable proof arrived not as a dramatic image, but as a faint, persistent hiss. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were struggling to eliminate a mysterious background noise from their sensitive antenna. They checked every system, cleaned every component, even evicting a pair of pigeons they suspected were causing the interference. But the hum remained, a uniform low-energy microwave signal coming from every direction in the sky. What they had accidentally discovered was the afterglow of creation itself, the cosmic microwave background, the cooled remnant radiation from the primordial fireball that had filled the universe in its earliest moments. It was the echo of the Big Bang, still resonating through space-time nearly 14 billion years later. With this discovery, the Big Bang theory solidified its place as the dominant cosmology. A detailed timeline was crafted, a story of cosmic evolution of breathtaking scope. It begins at time zero, a state of infinite density and temperature known as a singularity. In the first fraction of a second, an explosive expansion called inflation is thought to have stretched the universe from subatomic size to cosmic proportions. The fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, separated from a single unified force. A hot, dense soup of elementary particles filled the cosmos. For 380,000 years, this plasma was so dense that light was trapped within it, unable to travel freely. The universe was an opaque, searing fog. Then, as it continued to expand and cool, a momentous transition occurred. Electrons were captured by atomic nuclei, forming the first stable atoms of hydrogen and helium. Suddenly, the cosmos became transparent. Light was set free for the first time, and it is this primordial light that Penzias and Wilson detected as the cosmic microwave background. This was the beginning of the cosmic dark ages. The universe was filled with vast clouds of neutral gas, but there were no stars to illuminate it. According to our standard model, this darkness persisted for hundreds of millions of years. Gravity, the patient sculptor of the cosmos, slowly began its work. Tiny fluctuations in the density of the primordial gas, infinitesimally small variations visible today as temperature spots on the cosmic microwave background, acted as seeds. Denser regions began to pull in more and more material, growing larger and more massive over eons. This process was thought to be hierarchical and slow. First, small clumps of matter would coalesce, forming the first generation of stars, immense, brilliant, and short-lived behemoths composed of pure hydrogen and helium. These primordial suns would then group together into small protogalaxies. Over hundreds of millions, even billions of years, these smaller structures would collide and merge, gradually building up the large, majestic spiral and elliptical galaxies we see today. It is a story of patient construction, of small things gradually assembling into great ones. This was the narrative the James Webb Space Telescope was sent to confirm. Its powerful infrared vision was specifically designed to peer through the cosmic dust and capture the faint light of these very first small primitive galaxies taking shape. But Webb did not find what we expected. Instead of faint, messy, toddler-like galaxies slowly coalescing in the dawn of time, it found monsters. Within its first year of operation, astronomers using Webb discovered a number of galaxies that were shockingly massive and well-formed, at a time when they should not exist. Objects like Glass's 13, observed as it was just 300 million years after the Big Bang, appeared far more luminous and developed than our models of slow, hierarchical formation could explain. It was like looking into a nursery and finding fully grown adults. These early galaxies are not just bright. They seem to be teeming with older, redder stars, suggesting they had been furiously forming stars for a significant period already. Some appear to possess complex structures like galactic disks and bars, features that were thought to take billions of years to develop through gravitational interactions. To accommodate these findings within our current framework is extraordinarily difficult. The timeline is simply too compressed. You would need to form supermassive stars almost instantly after the Big Bang, have them collapse into black holes, and have those black holes grow at a rate that beggars belief to act as the gravitational anchors for such large early galaxies. Every step of the process would need to happen at maximum, almost physically impossible efficiency. The discrepancy is so profound that it has sent shockwaves through the astronomical community. Some scientists have begun to question the very foundations of the Standard Model. Is our understanding of galaxy formation fundamentally flawed? Or could the problem be even deeper? Could our understanding of the universe's expansion, the very redshifting of light we use to measure cosmic distance and time, be incomplete? Or does the existence of these impossibly ancient structures point to something else entirely? A past that extends beyond what we have long considered the absolute beginning. This is where the fear begins to creep in. Not a fear of monsters or aliens, but the vertiginous terror of realizing that the map of reality you have been using might be completely wrong. The existence of these mature, impossible galaxies could be the first empirical clue that the Big Bang was not the ultimate origin point. Perhaps it was just a moment of transition. A violent, transformative event, yes, but not a true genesis from nothing. If so, what could have triggered it? What could have existed before? Webb's data has flung open the doors to theories once relegated to the fringes of speculative science, forcing us to consider possibilities that shatter our deepest intuitions about time, space, and existence. One of the most elegant and compelling of these ideas is that of a cyclic universe. Imagine the entire history of our cosmos not as a straight line beginning at a single point, but as a circle, or more accurately, a continuous oscillation. In this model, our universe is just one iteration in an eternal series of universes. The theory proposes that the expansion we currently observe will not continue forever. Eventually, the mysterious force we call dark energy, which is responsible for accelerating the expansion, might weaken or even reverse its nature. If this were to happen, gravity would once again become the dominant force on a cosmic scale. The expansion would slow, halt, and then reverse. Galaxies would stop rushing away from each other and begin a long journey back together. Over billions of years, the universe would contract in a cosmic reversal of the Big Bang, an event dubbed the Big Crunch. Space would grow hotter and denser as all the matter and energy in the cosmos were drawn back towards a single focal point. In the final, catastrophic moments, galaxies would merge, stars would be ripped apart, and atoms themselves would be broken down into their constituent particles. The universe would return to the primordial, superheated, super-dense state from which it began. But crucially, in this model, it does not collapse into an inescapable singularity of infinite density. Instead, as the pressure and temperature reach an unimaginable peak, some new, unknown quantum gravitational force takes over, repelling everything and causing the universe to bounce. The Big Crunch would trigger a new Big Bang. A new universe, with perhaps slightly different physical laws, would be born from the ashes of the old. This Big Bounce concept is profoundly powerful. It elegantly removes the problematic singularity and the vexing question of a beginning. There was no beginning. There will be no final end. There is only the eternal cycle. In this context, the impossibly mature galaxies seen by Webb could be relics, structures or density fluctuations that somehow survived the transition from the previous cosmic epoch. They wouldn't have had to form from scratch in just a few 100 million years. They could be the inherited structures from a universe that existed for trillions of years before ours. The Big Bang, in this view, was not a creation event, but a cosmic reset button. To visualize this, think not of a single explosion in an empty void, but of a colossal lung, breathing in and out over timescales that dwarf human comprehension. Each exhalation is a Big Bang, an expanding universe like our own. Each inhalation is a Big Crunch, a collapse that gathers the raw materials for the next creation. Our existence is but a single breath in the life of an eternal oscillating cosmos. The scariness of this idea lies in its obliteration of our universe's specialness. Our entire 14 billion year history is just one chapter in an infinite book. And it carries the terrifying implication that our cosmos is destined for an apocalyptic end. A fiery collapse that will erase every star, every planet, and every trace of our existence, only to set the stage for the next, indifferent cycle. Another, perhaps even more mind-altering possibility, is suggested by theories of cosmic inflation. Inflation theory was originally proposed to solve some nagging problems with the standard Big Bang model, such as why the universe is so uniform and flat on large scales. It posits that in the first tiny fraction of a second, the universe underwent a period of hyper-accelerated expansion, growing exponentially in an instant. The physicist André Linde took this idea a step further with his model of eternal inflation. Linde proposed that this inflationary process, once started, never truly stops. Imagine a vast cosmic ocean of inflating space-time, a sort of energetic foam that is constantly expanding. Within this megaverse, some regions will randomly stop inflating and undergo a Big Bang, forming a pocket universe, a self-contained bubble of space and time. Our entire observable universe, everything we can ever see or know, would be just one of these bubbles in an infinite churning sea of cosmic creation. While our bubble universe began with our Big Bang 13.8 billion years ago, the larger meta-universe, the inflationary sea itself, may have no beginning and no end. In this scenario, Big Bangs are not unique events. They are happening constantly, all the time, all over the megaverse. Each bubble could have different fundamental constants of nature, different physical laws. Some might be stillborn, collapsing back on themselves in an instant. Some might be utterly barren, incapable of forming stars or complex chemistry. And some, like ours, might have just the right properties to allow for the emergence of galaxies, stars, and ultimately life. The trigger for our Big Bang, then, was simply a random quantum fluctuation in a pre-existing, eternally inflating substrate. It was a localized cessation of the hyperexpansion that allowed energy to convert into the matter and radiation that fills our cosmos. This framework, known as the multiverse, is both exhilarating and terrifying. It suggests that the laws of nature that we hold so sacred might not be fundamental, but merely the local bylaws of our particular cosmic bubble. The impossible galaxies seen by Webb could be a sign that our bubble interacted or collided with another in its early history, seeding it with structures or energy that accelerated its development. The psychological impact of this idea is profound. It decenters humanity in the most dramatic way imaginable. Not only are we not at the center of our solar system, or our galaxy, or even our universe, we might be inhabitants of a single, unremarkable bubble among an infinite number of others. Our existence becomes a matter of statistical probability, a lottery ticket drawn in a cosmic casino of incomprehensible scale. The scary aspect here is one of existential vertigo. If there are infinite universes with infinite variations, then every possible outcome exists somewhere. Our lives, our choices, our entire history are just one permutation in an endless array. It dilutes the meaning we seek in our own existence to near zero. But perhaps the most exotic and challenging explanation comes from the frontiers of theoretical physics, from the mind-bending world of string theory and M-theory. These frameworks attempt to unite quantum mechanics and general relativity into a single, all-encompassing theory of everything. They propose that the fundamental constituents of reality are not point-like particles, but tiny, vibrating one-dimensional strings. And most critically, these theories require the existence of extra dimensions of space, beyond the three we experience in our daily lives. In one popular version of this idea, called the ekpyrotic or brain world scenario, our entire four-dimensional universe, three of space, one of time, is a membrane, or brain, floating within a higher dimensional space, often called the bulk. Imagine two vast parallel sheets of paper drifting in a three-dimensional room. Our universe is one of those sheets. In this model, there could be another brain, another universe, floating parallel to our own, perhaps only a microscopic distance away in a dimension we cannot perceive. These brains are not necessarily static. They can move, ripple, and occasionally collide. According to this theory, the Big Bang was not a beginning from a singularity, but the result of a cataclysmic collision between two of these parallel universes. The unimaginable kinetic energy of this cosmic clap would be converted into the matter and radiation that filled our newly energized universe, kick-starting its expansion. The shock wave of the collision would create the initial conditions, the tiny fluctuations and immense heat that we observe as the aftermath of our Big Bang. This model provides a physical mechanism, a trigger for the birth of our cosmos. It was an event, a collision, in a pre-existing higher dimensional space. The early overly massive galaxies Webb has observed could be a consequence of the specific nature of this brain collision. Perhaps the impact was not perfectly uniform, creating hotspots, or massive gravitational seeds that allowed structures to form much more rapidly than a standard Big Bang would permit. The fear induced by this theory is one of incomprehensible scale and power. It suggests we live on a fragile membrane, adrift in an unseen reality of higher dimensions, potentially subject to cosmic events of a violence we can barely conceptualize. Our very existence could be the result of a random, inter-universal car crash. So, We are left standing at a monumental crossroads. The James Webb Space Telescope, our greatest eye on the cosmos, has shown us a picture of the early universe that is at odds with our most cherished story. The data is a whisper that is growing into a roar, forcing us to confront possibilities that were once the domain of science fiction. Did the Big Bang spring from the ashes of a previous collapsed universe? Is our entire cosmos but one bubble in an infinite effervescent multiverse? Or was our reality born from the violent collision of unseen dimensions? Each of these possibilities is profoundly unsettling. They dismantle the comforting idea of a single special creation event. They suggest that time may not have had a beginning, and that space is far larger and stranger than we ever imagined. This is the true terror. It is the realization that the universe does not owe us a simple, human-scale explanation. The reality of existence may be something that is fundamentally beyond our innate capacity to intuit or comprehend. We are like ants on a single grain of sand, trying to understand the concept of a beach, an ocean, and a planet, based solely on the evidence of our immediate surroundings. And yet, this is also where the wonder lies. The fact that we, a species of primates on a small rocky world, can build a machine like the Webb telescope, send it 1,000,000 miles into space, and use it to ask these ultimate questions is a miracle in itself. The scary data is not an endpoint, it is a new beginning. It is an invitation to be bolder in our thinking, to push the boundaries of our theories, and to embrace the sublime mystery of it all. The work is far from over. Astronomers are now scrambling to confirm these early findings, to gather more data, to look even farther back in time. Every new image from Webb is another piece of an immense cosmic puzzle. The scientists who analyze this data are pioneers, charting an unknown territory at the very edge of time. They are working to determine if these early massive galaxies are truly as common as they seem, or if we have simply been lucky or unlucky in our first observations. They are developing new models to see if the standard theory can be tweaked or stretched to accommodate these cosmic anomalies, or if it must be abandoned entirely. This is the very essence of the scientific process. It is a constant dialogue between theory and observation. For a century, theory has led the way, with observation struggling to catch up and confirm its predictions. Now, for the first time in modern cosmology, observation has leapt ahead. The James Webb Space Telescope has given us a direct message from the cosmic dawn, and we do not yet understand the language it is speaking. It is humbling, it is exhilarating, and yes, it is a little bit frightening. We may never know with absolute certainty what triggered the Big Bang, or what, if anything, came before. These questions may lie on the other side of a physical horizon we can never cross, shrouded by the incandescent glare of creation's firewall. But Webb has given us a tantalizing, terrifying glimpse beyond the veil. It has shown us that the universe is not just stranger than we imagine, it is stranger than we can imagine. The golden eye continues its silent vigil, gathering the faint ghostly light from an era we thought we knew. With each photon it collects, it adds another word to a new story of creation that is yet to be fully written. The journey into the past is a journey into the unknown. And while the destination is uncertain, one thing is clear. We have entered a new age of discovery, an era where our most fundamental understanding of our own cosmic origins is being challenged. The ground beneath our feet, the very fabric of space-time, feels a little less solid than it did before, and for those who dare to look, the view is terrifyingly beautiful. What is a beginning? Is it a single, explosive moment from which all of time and space unspools like a golden thread, or is it something more subtle, a slow awakening from an unknowable silence? For generations we have carried a story within us, a grand cosmic narrative of our origins. It is a story of magnificent simplicity of a universe born in fire and fury, a sterile crucible containing only the lightest, most elementary ingredients. A universe of hydrogen, an ocean of it spiced with a touch of helium, and an almost imperceptible whisper of lithium. This was the universe as we understood it, the universe as our most elegant theories demanded it to be. For nearly 14 billion years, this foundational chapter of our cosmic story has been our anchor, a truth carved into the bedrock of astrophysics. It told us that complexity was a reward earned over vast, almost unimaginable stretches of time. The elements of life, the carbon in our cells, the oxygen we breathe, were not present at the creation. They had to be forged. They were the children of stellar death, the ashes of giant suns that had to first assemble from primordial gas, ignite their nuclear hearts and burn for millions of years before collapsing under their own colossal weight. Only then, in their final cataclysmic supernova explosions, would these heavier elements be blasted into the void, seeding the next generation of stars and planets with the raw materials for chemistry, for geology, for biology. This was the great, slow generational cycle of the cosmos, a universe learning to build step by laborious step over eons. From the simple came the complex. From the barren came the fertile. It was a beautiful story, a logical story, and as we now know, it was a profoundly incomplete one. We thought we knew the timetable of creation. We believed we had deciphered the recipe for the cosmos. We were about to learn how little we truly understood about the first lines of the first page. To read that page, to witness the universe in its infancy, we needed more than a story. We needed a machine capable of looking back in time, not figuratively, but literally. Every telescope is a time machine. Light, even at its blistering speed, takes time to travel. To see a galaxy 1 billion light-years away is to see it as it was 1 billion years ago. But the dawn of the cosmos, that first flicker of starlight after the Big Bang's afterglow faded, was an almost mythical distance away. 13.5 billion years in the past. The light from that era is ancient, stretched and exhausted by its immense journey across an expanding universe. It has been pulled from the visible spectrum into the infrared, a form of light that is less a colour and more a heat signature, an echo of a fire that went out long ago. To see this fossil light, we had to build an eye unlike any other. An instrument of impossible precision shielded from the warmth of our own sun, our own Earth, even our own moon. We built the James Webb Space Telescope, not merely as a successor to Hubble, but as a different kind of being entirely. Its segmented mirror, a breathtaking honeycomb of 18 gold-plated hexagons, was engineered to capture the faintest whispers from the edge of time. We sent this magnificent golden eye 1 million miles from home to a gravitationally stable point in the void where it could cool to a near absolute zero, becoming so cold that its own faint heat would not blind it to the ancient warmth it sought. It was a pilgrimage, humanity's most sophisticated emissary sent on a multi-billion-dollar quest to the beginning of everything to watch the first galaxies ignite and confirm the beautiful logical story we had told ourselves for a century. The first images that returned were everything we had hoped for and so much more. They were tapestries of cosmic grandeur, fields of view, littered not with a handful of galaxies, but with thousands upon thousands. Each pinprick of light, each faint red smudge was an island universe, some so distant, their light had been travelling since before the Earth itself had even formed. We were staring at the cosmic dawn. Our theories were about to be put to the ultimate test. We were ready to witness the universe as a simple, pristine nursery of hydrogen and helium. We were prepared to see the first awkward stumbling steps of cosmic evolution. What we were not prepared for, what no theory could have possibly predicted, was the ghost in the data. Among those nascent galaxies, mere infants by cosmic standards, some existing just 300 million years after the Big Bang, a shockingly small sliver of time, we began to analyse their light. Using Webb's advanced spectrographs, we could perform a kind of cosmic archaeology. We could take the faint ancient light from a single galaxy and shatter it into its constituent wavelengths, spreading it out like a rainbow. This spectrum is a galaxy's fingerprint. It is a barcode containing an astonishing amount of information, revealing not just its distance and its age, but its very chemical composition. Each element, each molecule absorbs and emits light at specific, unique frequencies, leaving dark absorption lines or bright emission lines in the spectrum. It is an unambiguous signature, a message from the past written in the language of light. As we had predicted, the fingerprints of hydrogen and helium were everywhere, bold and clear, the dominant signature of that primordial era. But then, as our instruments stared longer and our scientists refined the data, something else began to emerge from the noise. It was a subtle signal, a series of spectral bumps and wiggles in a place we expected to find nothing but a flat, featureless line. At first it was dismissed as an anomaly, an instrumental artifact, a phantom, but it refused to disappear. It appeared again in another galaxy and then another. It was real, and its identity sent a shockwave through the global astronomical community. These were the unmistakable spectral fingerprints of polycyclic aromatic hydrocarbons, or PAHs. It is a complex name for a family of molecules you're surprisingly familiar with. They are found in the soot from a candle flame, in the char of a barbecue grill, in the exhaust from a car. They are rugged ring-shaped molecules made of carbon and hydrogen, some of the most complex and widespread organic molecules known in our own Milky Way galaxy. They are in a sense the molecular bedrock of complex chemistry. In our corner of the universe they are everywhere. But finding them there in the murky twilight of cosmic dawn was not just surprising. It was impossible. Let us be absolutely clear about the scale of this impossibility, for it strikes at the very heart of our understanding. To build a PH you need a healthy supply of carbon atoms, and as our foundational story tells us, carbon is not a primordial element. It did not emerge from the Big Bang. It must be manufactured deep inside the nuclear furnaces of massive stars. This process takes time. A star has to be born from a cloud of simple hydrogen and helium. It has to grow, stabilize, and begin fusing hydrogen into helium in its core. For millions of years it burns slowly, building up a core of heavier elements. Only in the final violent stages of its life, or in its explosive death, as a supernova, is that precious life-giving carbon ejected into the interstellar medium. But the process does not stop there. That newly forged carbon floating in the void is still just a collection of individual atoms. To assemble into complex structures like PAHs, it needs a suitable environment. It needs to cool down. It needs to find its way into dense, cold, dusty clouds of gas where atoms can stick together, sheltered from the destructive ultraviolet radiation of nearby stars. Within these stellar nurseries over yet more vast stretches of time, a rich and complex organic chemistry can slowly take root, with carbon atoms linking up with hydrogen to form these intricate rings. The entire supply chain from the birth of a star to its death, to the scattering of its ashes, to the slow cooking of those ashes into complex molecules, was believed to require a minimum of several 100 million and more likely over 1 billion years. It was a stately multi-generational cosmic process. Yet the James Webb Space Telescope was showing us these very molecules fully formed and in startling abundance in galaxies that were only 300 to 400 million years old. The timeline was shattered. The universal clock was broken. It was like finding a fully built skyscraper complete with plumbing and electricity on a construction site just minutes after the groundbreaking ceremony. All the necessary steps, all the required time had been bypassed in a way we simply could not explain. The universe's chemical factory had somehow skipped the entire development phase and jumped straight to mass production. This discovery does more than just add a new footnote to our textbooks. It forces us to rip out entire chapters and question the fundamental assumptions we have held for decades. The neat linear progression we had envisioned from Big Bang to simple elements, to first stars to heavy elements, to complex molecules has been revealed as a gross oversimplification. The early universe was not the pristine, chemically naive place we had imagined. It was against all odds, already seeded with the kind of molecular complexity we thought was a modern invention. This single, staggering observation throws a cascade of new urgent questions at us. How did this happen? Was there a flaw in our understanding of the first generation of stars, the so-called population 3 stars? These theoretical behemoths, composed only of primordial hydrogen and helium, were thought to live fast and die young. Could they have somehow synthesized and distributed carbon with an efficiency far beyond what our models predict? Did they operate by a different set of rules, creating a kind of stellar fast track for heavy element production that we have never before conceived? Or perhaps the answer lies not in the stars, but in the space between them. Could there be an unknown chemical pathway, a way to build complex organic molecules directly in the turbulent hot outflows of the very first galaxies bypassing the need for those cold, dusty clouds entirely, a form of high-speed shock-front chemistry that works in conditions we previously considered utterly hostile to molecular formation. The implications are dizzying. These PA8s are more than just cosmic soot. On planets like our own, they are thought to be key ingredients in the primordial soup from which life itself emerged. They are a crucial step on the ladder of complexity that leads from simple chemistry to living biology. To find them so early in cosmic history means that the universe was potentially fertile, ready for life billions of years earlier than we ever dared to imagine. The window of opportunity for life to begin in the cosmos may not have opened with a gentle creak, but may have been thrown wide open almost as soon as the first lights in the universe switched on. The elegant story of a slow, methodical creation has been replaced by a thrilling, chaotic mystery. The James Webb Space Telescope, built to confirm our vision of the past, has instead revealed a history far stranger and more wonderful than we could have invented. We are now like explorers who, expecting to find a barren desert, have stumbled upon a lush, sprawling jungle, teeming with unknown life. The pristine nursery was in fact already a workshop, humming with a chemical creativity that defies our explanations. Those faint red smudges in Webb's deep fields are no longer just markers of distance and time. They are clues to a lost chapter of our origin story. They are evidence of an ancient accelerated path to complexity that was hiding in plain sight, waiting for an eye sharp enough to see it. The discovery of these impossible molecules is not an endpoint. It is not an answer. It is a spectacular, resounding invitation. An invitation to rethink everything we thought we knew about how the universe builds, grows, and comes alive. To solve this puzzle, we must now journey back into that primordial furnace. We must chase these molecular ghosts through the dawn of time, following the unexpected chemical breadcrumbs they have left for us. We must abandon our old maps of creation and venture into a wild, uncharted territory, seeking to understand the secret chemistry of the first light. The story of our beginning has just become infinitely more interesting. Every story has a beginning, but the universe's first chapter was written in invisible ink. Before the first dawn, before the first galaxy swirled into existence, there was an age of profound, unending darkness. To understand the revolution now unfolding in our telescopes, you must first journey back with us into that silence. You must picture a cosmos stripped of all its familiar jewels, a void so fundamentally different from our own that it challenges the very definition of a universe. We are going back to the beginning, to a time when the cosmos was a blank canvas, holding only the promise of what it might one day become. For hundreds of millions of years after the Big Bang's fading afterglow, this was the state of reality. The explosive birth cry of creation had subsided. Its light stretched and cooled into a faint microwave hum that filled all of space, a final ghostly echo of a time of unimaginable heat and density. As this primordial plasma cooled, the universe performed its first great act of construction. Electrons once buzzing freely in a superheated soup were finally captured by protons and helium nuclei. This monumental event known as recombination transformed the cosmos. The universe, once an opaque fog of charged particles, became transparent for the very first time. But this newfound clarity revealed nothing. There were no stars to pierce the gloom, no galaxies to pinwheel across the emptiness. There was only gas. Unfathomably vast, cold, and lonely clouds of hydrogen and helium, the two simplest elements forged in the Big Bang's crucible, now drifted in a darkness that would persist for an eternity by human standards. This was the true dawn of the cosmic dark ages. It was not an empty void, but a universe full of matter, yet utterly devoid of light. Imagine yourself floating in this nascent cosmos. The silence would be absolute, broken only by the whisper of gravity itself. All around you, stretching for light years in every direction, is a thin, featureless mist of neutral hydrogen. It is cold, barely a few degrees above absolute zero, and it is overwhelmingly simple. The chemical palette of this universe contained only 3 colors, hydrogen the most abundant element by far, helium its stable and unreactive cousin, and a trace almost negligible amount of lithium, an element so insignificant in the grand scheme that it was little more than a rounding error. This was it. The entire inventory of ingredients available to build everything that would ever exist. There was no carbon for life, no oxygen for water, no silicon for rock. The very building blocks of our world, of our bodies, were absent, locked away in a future that was not yet guaranteed. This period represents one of the great frontiers of modern cosmology, a time we have long tried to model and understand, yet could never directly see. It was a ghost in our cosmic history, a chapter we knew had to exist, but whose pages were completely blank. For over 100 million years, gravity was the only artist, the universe's only engine of change. Patiently, relentlessly, it sculpted these vast invisible clouds of primordial gas. In the infinitesimally denser regions of the cosmic web, a slow motion collapse began. Gravity, the weakest of nature's forces, worked on a scale so immense that its gentle, persistent pull was all that mattered. It gathered the hydrogen and helium atoms, pulling them from the diffuse fog into ever denser filaments and knots. Think of it as the universe holding its breath, gathering its strength for its next great act. For millions of years, these proto-galactic clouds grew compacting under their own immense weight, their cores becoming hotter and denser. This was the cosmic nursery, but it was a harsh and unforgiving one, operating in complete darkness with only the simplest raw materials. The stage was being set for a monumental transformation, the moment the universe would make its own light for the very first time. The end of the Dark Ages was approaching, not with a gentle sunrise, but with a cataclysm of unimaginable violence. Deep within the hearts of the densest gas clouds, the pressure and temperature finally reached a critical threshold, a point of no return, 10 million degrees. In that instant, nuclear fusion ignited. The first stars were born. But these were not the familiar placid stars that dot our night sky. These were population 3 stars, a generation of celestial objects that has long been extinct and which we have never directly observed. They were monsters, forged from pure hydrogen and helium without the heavier elements that help modern stars regulate their burning. They were fantastically unstable and breathtakingly massive. Some may have swelled to hundreds, perhaps even 1,000 times the mass of our own sun. They were not yellow or orange, but a brilliant searing blue-white. They didn't just shine, they raged. A single population 3 star could be millions of times more luminous than our sun, blazing with an intensity that defies easy comparison. When these first stellar behemoths ignited, they didn't just end the cosmic dark ages, they shattered the darkness. Across the universe, pockets of intense, ferocious light tore through the primordial fog. This new light, however, was not a gentle, life-giving glow. It was a sterilizing, destructive force. These massive stars burned through their nuclear fuel at a furious pace, living for only a few million years, a fleeting instant in cosmic time. Throughout their short, violent lives, they blasted their surroundings with torrents of high-energy ultraviolet radiation. This was not the gentle UV that gives you a sunburn. This was a celestial blowtorch, a source of radiation so powerful it could rip electrons clean off the atoms in the surrounding gas, a process called reionization. This radiation would have been lethal to any form of complex chemistry, acting as a relentless cosmic sterilizer. Any fragile fledgling molecules that might have tentatively formed in the cold darkness would have been instantly obliterated by this onslaught. The very light that ended the darkness also ensured that the universe remained a chemical wasteland. The environment of the early cosmos was a paradox of creation and destruction. While the first stars brought light, they also reinforced the profound simplicity of their surroundings. The universe was now a place of extremes. In the immediate vicinity of these stellar monsters, it was a cauldron of high-energy radiation, a place where only the most basic atomic structures could survive. Further out, the vast majority of the cosmos remained cold, dark, and chemically pristine, still composed of little more than hydrogen and helium. The conditions for complexity simply did not exist. To build interesting molecules, you need 2 fundamental things: a diverse set of atomic building blocks and stable protected environments where those blocks can link together. This early universe had neither. It possessed a brutally limited chemical alphabet and an environment of relentless molecule-shattering violence. Any hope for chemical evolution for the first stirrings of the complexity that would one day lead to planets, and people had to wait for these first stars to die, and they died as spectacularly as they lived. After exhausting the fuel in their cores, these giants collapsed under their own colossal gravity and exploded in the most powerful cataclysms the universe had ever known, the first supernovae. These were not just explosions, they were acts of cosmic alchemy. In the unimaginable heat and pressure of their death throes, these stars performed a miracle. For the very first time, they fused hydrogen and helium into heavier elements: carbon, oxygen, nitrogen, silicon, iron. The very elements that form the bedrock of our world were forged in these celestial furnaces and hurled out into the void. This was the universe's first seeding, the first time the cosmos was enriched with the ingredients for something more interesting than simple gas. The ashes of these dead stars became the seeds of the next generation. They were, in the most literal sense, our creators. Without these first violent deaths, the universe would have remained a simple, sterile place forever. Yet this crucial act of enrichment must be viewed in its proper cosmic perspective. The universe is vast, and these first supernovae were few and far between. Imagine dropping a single pinch of coloured sand into an entire ocean. While the elements for complexity now technically existed, they were spread so thinly as to be almost non-existent. The concentration of these metals, as astronomers call all elements heavier than helium, was infinitesimal. The cosmos was still, by any reasonable measure, a chemical desert. The average patch of intergalactic space would have remained more than 99.999% hydrogen and helium. Finding a carbon or oxygen atom would have been an event of incredible rarity. It was a universe seasoned with only the faintest whisper of potential. This profound scarcity was the first great barrier to the formation of complex molecules. You cannot build intricate structures when the necessary bricks are separated by millions of miles of empty space. The second barrier was the lingering hostile environment. Even as the first stars died, others were being born, continuing to flood their surroundings with destructive ultraviolet radiation. The universe was still a battlefield of competing forces. The gentle pull of chemistry, which seeks to bind atoms together into molecules, was hopelessly outmatched by the violent push of stellar radiation, which rips them apart. Any two atoms that happen to find each other and form a tentative bond, say a carbon and an oxygen atom, would be almost instantly blasted apart. For complex molecules to form, especially the large organic ones that are the precursors to life, you need shelter. You need cosmic nurseries, dense clouds of gas and dust that can shield fragile developing chemistry from the harsh glare of nearby stars. But in this early epoch there was no dust. Cosmic dust, the tiny grains of silicate and carbon that are essential for molecular formation in our own galaxy, is itself a product of many generations of star birth and death. It simply had not had time to accumulate. This then was the prevailing and entirely logical scientific consensus for decades. The early universe, for at least the first billion years of its existence, was a place fundamentally hostile to chemical complexity. It was too simple, too violent, and too transparent. The ingredients were too scarce. The environment was too harsh. The shelters did not exist. Models of cosmic evolution built on our best understanding of physics and chemistry all pointed to the same conclusion: significant molecular creation, especially of complex organic compounds, was an event that belonged to a much later, more mature and more chemically enriched universe. It was something that should happen in galaxies like our own Milky Way, where countless generations of stars have lived and died, seeding the cosmos with a rich abundance of heavy elements and thick protective dust clouds. To suggest that such molecules could exist in the cosmic dawn was not just unlikely, it was by all reasonable accounts impossible. It would be like trying to build a modern city with only wood and stone during a perpetual hurricane with your building materials scattered across an entire continent. The task seems absurd on its face, so we looked back in time with our telescopes with Hubble and with instruments on the ground, and what we saw seemed to confirm this picture. We saw the first small clumpy galaxies beginning to form, glowing with the fierce light of young hot stars. We measured their chemical composition and found them to be overwhelmingly metal-poor, just as the theories predicted. The story was consistent, elegant, and powerful. The universe started simple and grew complex over time. It was a gradual, stately evolution, a slow enrichment over billions of years that eventually paved the way for the intricate chemistry we see around us today. This narrative became the bedrock of our understanding of cosmic origins. It was the story we told ourselves, the one that every piece of evidence seemed to support. It was a story of a barren, violent youth followed by a slow, patient maturation into the rich, life-bearing cosmos we inhabit. Our models became more and more sophisticated, simulating the birth of the first stars, the impact of their radiation, and the slow spread of the first heavy elements with stunning precision. Every simulation reinforced the same core truth. The first billion years were the age of atoms, not the age of molecules. The universe was simply not ready. It lacked the raw materials, the requisite safety, and the necessary time to begin the work of complex construction. This was not a guess. It was the firm conclusion drawn from decades of painstaking research, observation, and theoretical work. It was a cornerstone of modern astrophysics. The idea of finding a complex molecule like a polycyclic aromatic hydrocarbon, a dusty organic soot molecule that we find in star-forming regions today, in a galaxy from this era, was patently absurd. It would violate our fundamental understanding of how chemical complexity evolves in the cosmos. It would be a discovery that had no right to exist. And so, as we prepared to launch a new eye into the heavens, an infrared telescope of unprecedented power, capable of peering deeper into this ancient epoch than ever before, our expectations were clear. We expected to see the first infant galaxies in sharper detail. We hoped to catch a glimpse of the earliest star clusters, perhaps even the glow from the reionization process itself. We were looking for the first chapters of the story we already knew, hoping to fill in the details on a narrative whose broad strokes were already firmly in place. No one was seriously looking for the chemical signatures of complex organic molecules. No one dared to. To even propose such an observation would have seemed a waste of precious telescope time, a search for something that our models and all prior evidence told us could not possibly be there. In this brutal and elementary cosmos, a place of raw hydrogen and stellar fire, where could the seeds of impossible complexity possibly hide? The answer, we were all but certain, was nowhere. To solve a puzzle buried 13 billion years in the past, a riddle written in the light of the universe's first dawn, we first had to conquer a challenge of the present. We had to build a time machine, not of gears and spinning dials, but of gold-plated beryllium cryogenic coolers and a sunshield the size of a tennis court. A machine designed to unfold with impossible grace 1,000,000 miles from the world that created it. The James Webb Space Telescope was more than an observatory. It was humanity's most audacious gamble, a multi-billion-dollar promissory note sent to the cosmos payable only in knowledge. Its launch was not a quiet departure. It was a controlled cataclysm, a thundering ascent on a column of fire that ripped through the humid air of French Guiana, every vibration a potential point of failure for the impossibly delicate instrument folded within its payload fairing. For the thousands of scientists and engineers who had poured their lives into its construction, these were moments of exquisite terror. Decades of work, the future of astrophysics, all riding on the mathematical perfection of a rocket's trajectory. As it climbed a brilliant star of our own making, it carried the collective hope of a species desperate to understand its own origins. The journey that followed was a silent month-long ballet through the void, a coast towards a unique point of gravitational equilibrium known as Lagrange Point 2. This is not a place, but a condition, a stable perch in space where the gravitational pull of the Sun and Earth balance perfectly, allowing the telescope to orbit the Sun in lockstep with our own planet. It is a place of profound cold and darkness, far from the thermal glare and radiative noise of Earth, the perfect celestial blind from which to hunt for the faint ancient light of the cosmic dawn. But arriving there was only the beginning. The true test, the sequence of events that held thousands of careers in the balance, was the unfurling. This was cosmic origami on a scale never before attempted. Stowed for launch, Webb was a dense, compact package of latent potential. To become the eye it was designed to be, it had to blossom in the vacuum. First came the sunshield, the most critical and complex component. 5 layers of a gossamer-thin material called Captain, each no thicker than a human hair, had to be meticulously pulled taut by a system of motors, cables, and pulleys. Any snag, any tear, any failure in the tensioning process would have been catastrophic, blinding the telescope with its own heat and the sun's unyielding radiation. For weeks the world watched, holding its breath as mission controllers sent commands across 1,000,000 miles of empty space, guiding the deployment of this vast silver kite. It was a slow, deliberate process, a technological miracle performed in absolute silence, a shield against the light so that we might see the first light. Once the shield was in place, securing the telescope in permanent cryogenic shadow, the real heart of the machine could be revealed. The primary mirror, a breathtaking honeycomb of 18 hexagonal gold-coated segments, began its own delicate deployment. 2 side wings folded back for the launch swung forward and latched into place, completing the immense 6.5-metre light-collecting surface. Each individual segment, a marvel of engineering, then had to be adjusted with astonishing precision. Actuators moving in steps measured in nanometers, a fraction of the wavelength of light itself, began a months-long process of alignment, focusing the 18 separate images into a single perfect point of light. This wasn't merely assembly. It was the awakening of a new sense for humanity. We were teaching our creation how to see aligning its golden eye to resolve the faintest whispers from the edge of time. The telescope was now structurally complete, but its scientific journey had yet to begin. To see the universe in the specific language it was built to understand, the language of infrared, it had to become colder than any natural place in our solar system. The universe's expansion, the very phenomenon we want to study, stretches the light from the first galaxies. What may have begun as visible, even ultraviolet light has travelled for so long, and across such an expanding distance, that its wavelength has been stretched redshifted all the way into the infrared spectrum. This is the light of creation, and to our eyes it's invisible. It is in essence heat. For Webb to see this faint primordial warmth, it had to be fantastically cold itself, ensuring its own thermal signature wouldn't drown out the celestial signal. The sunshield brought the cold side down to a frigid minus 233 degrees Celsius, but for some instruments even that wasn't enough. The mid-infrared instrument or MIRI required a dedicated cryocooler and advanced refrigeration system that actively pumped its temperature down to a breathtaking 7 degrees above absolute zero. At this temperature, the very vibration of atoms is nearly silenced. The telescope had become a perfect sensor, a gravitational and thermal ghost floating through the solar system, blind to the sun at its back, deaf to the noise of our world, its gaze fixed entirely on the deep past. And then, after 6 months of travel, deployment, alignment, and cooling, the moment arrived. The first photons, ancient travellers on a 13-billion-year journey, finally found their destination on the pristine golden surface of Webb's mirror. They were funneled down to the detectors, their energy converted into electrons and the electrons into data. On Earth, that data resolved into an image. It wasn't one of the breathtaking vistas that would later capture the world's imagination. It was a simple calibration field of stars, a test pattern. But to the teams in the control room, it was everything. It was sharp. It was clear. It worked. The gamble had paid off. The eye was open. The time machine was online. The initial excitement was palpable, a wave of relief and elation that rippled through the global astronomical community. The first publicly released images, the cosmic cliffs of the Carina Nebula, and the intricate dance of Stephan's quintet were a stunning demonstration of the telescope's power. They were sharper, deeper, and more detailed than anything that had come before, revealing hidden, star-forming regions and galactic structures with unprecedented clarity. But these were relatively close cosmically speaking. They were the warm-up act. The main event, the entire reason for Webb's existence, was the hunt for the first-light galaxies, the earliest collections of stars to ignite after the Big Bang objects whose light is so profoundly redshifted, it exists only as an infrared whisper. The search began with the deep field programs. Webb stared at a patch of sky that appeared utterly black and empty to all previous telescopes, a region no bigger than a grain of sand held at arm's length. For hundreds of hours it drank in the faint ancient light, accumulating photons one by one. When the data was processed, that patch of darkness was revealed to be teeming with life, a cosmic zoo populated by thousands of galaxies. Most were faint red smudges, their light stretched to the breaking point by cosmic expansion. These were the targets. These were the relics from the universe's infancy. But pretty pictures were not the ultimate goal. The real secrets were not in the shape or size of these galaxies, but encoded within their light. This is where the true power of Webb's instrumentation comes into play, a technique known as spectroscopy. If an image tells you what something looks like, a spectrum tells you what it is. By passing the light from a single galaxy or quasar through a prism or grating, astronomers can spread it out into its constituent colours, a rainbow of infrared light. But this rainbow is not smooth. It is interrupted by a series of sharp, dark lines, and sometimes bright, glowing ones. This is a cosmic barcode. Every element, every molecule in the universe absorbs and emits light at specific, unique frequencies. Hydrogen leaves one pattern of lines, helium another. Oxygen, carbon, neon, they all have an unmistakable spectral fingerprint. By reading this barcode, we can determine the precise chemical composition of an object, billions of light years away. We can measure its temperature, its density, even how fast it's moving away from us. It is the most powerful tool we have for understanding the cosmos. So as the data from the very first highest redshift galaxies began to stream back to Earth, teams of scientists gathered around their screens, their work beginning in earnest. They were the universe's cryptographers, tasked with decoding these messages from a lost era. The initial analyses were confirming. They pointed their spectrographs at a galaxy candidate catalogued as Sears 93316, an object seen as it was just 250 million years after the Big Bang. Its spectrum was a textbook example of what they expected to find. The barcode was clear, the bold, unmistakable lines of hydrogen, the more subtle signature of helium. It was a pristine primordial object, a galaxy made of the simple raw ingredients forged in the Big Bang. This was the baseline, the standard model of early cosmic chemistry made manifest. It was a triumphant validation of decades of cosmological theory. But science rarely proceeds along such a clean straight line. As the teams began analysing more and more of these distant targets, whispers of something strange began to circulate through the research groups. It started subtly. An analyst at a university in Germany working late into the night stares at a spectrum from a quasar, the intensely luminous core of an infant galaxy, powered by a supermassive black hole. The primary lines of hydrogen are there, of course, blazing bright. But there's something else, a small unexpected peak in a region of the spectrum where nothing was supposed to be. It's faint, barely rising above the background noise. She runs the diagnostic software again, recalibrates the baseline. The peak remains. She flags it as a potential artifact, a possible detector flaw, or a miscalculation in the complex software that corrects for the light's long journey. In another institution, a graduate student in California is analysing the diffuse halo of gas surrounding a different ancient galaxy. He's looking for the absorption lines that indicate what kind of material the galaxy is feeding on. He finds the expected hydrogen and helium, but his models keep failing to perfectly fit the data. There's a series of shallow absorption troughs, a faint stutter in the barcode that doesn't correspond to any simple element. He spends a week trying to eliminate it, convinced it's an error in his own code. He can't. The signal, however weak, is persistent. These were isolated incidents, the kind of instrumental quirks and unexplained noise that are common in any new groundbreaking observatory. The standard procedure is to be skeptical, to rigorously attempt to disprove your own findings before claiming a discovery. Could it be an unaccounted-for atmospheric line from Earth unlikely, given Webb's position in space? Could it be a zodiacal light artifact, the faint glow of dust within our own solar system? The teams developed sophisticated models to subtract this foreground contamination, and the anomalies persisted. The meticulous process of verification began on a global scale. Different teams, using different analytical software and processing pipelines, were asked to look at the same raw data, a form of scientific peer review, happening in near real time. The suspense was building not in a dramatic flurry, but in the quiet, methodical work of cross-checking, reanalyzing, and endless debate over teleconference calls spanning multiple continents. The question hung in the air, were these just ghosts in the machine, or was the machine showing them ghosts from the dawn of time? The turning point came when the signals started to correlate. The strange emission peak seen in the German data appeared at a similar wavelength to the unexplained absorption troughs in the Californian data. Then a third team analysing a gravitational lens where the gravity of a massive foreground galaxy cluster magnifies the light from an even more distant object behind it, found the same spectral features, this time amplified and clearer. This was no longer a collection of isolated curiosities. This was a pattern. The signal was real. And it was terrifying. Because the barcode, this faint repeating fingerprint appearing in the light from the most ancient structures in the cosmos, did not belong to an element. Simple atoms like carbon or oxygen have their own well-understood signatures, and this wasn't it. The complexity of the pattern, the specific spacing and relative strengths of the lines, hinted at something far more intricate. It was the unmistakable signature of a polyatomic molecule, a complex structure of atoms bonded together. More than that, the best-fit models suggested a molecule containing carbon, a cornerstone of organic chemistry. These were not the simple chemical building blocks predicted by the standard cosmological model. The universe, a mere few hundred million years after the Big Bang, was supposed to be a chemically impoverished place, a simple soup of hydrogen and helium, with only the barest trace elements forged in the hearts of the very first short-lived supergiant stars. To form complex molecules, especially those involving carbon, you need multiple generations of star birth and death to enrich the cosmos with heavy elements. You need time. You need planetary nebulae and supernova shockwaves to seed the interstellar medium. You need dusty protected molecular clouds where these atoms can meet and bond. You need, in short, a mature chemically evolved galaxy. Yet here were the spectral ghosts of these compounds, haunting the light from the very first quasars and galaxies objects that existed when the universe was less than 5% of its current age. The data was irrefutable, yet the conclusion was impossible. It was like finding a Roman coin inside a sealed Egyptian pyramid, a temporal paradox written into the light of the cosmos. The meticulous analysis had not solved a mystery, it had deepened it profoundly. The time machine was not just showing them the past we expected to see. It was revealing a history of our universe that by all rights should never have happened. That single shimmering line in the data was more than an anomaly. It was a ghost, a chemical spectre haunting the very dawn of time, whispering a language that, according to everything we knew, had not yet been invented. On screens in Baltimore, in Pasadena, and in laboratories scattered across the globe, astronomers stared at the same defiant signature. It was a pattern of light and shadow, an absorption profile carved from the ancient starlight of a galaxy over 13 billion light-years away. Yet it was a pattern they recognized with unnerving familiarity. It was the intricate, unmistakable fingerprint of complex carbon. Specifically, it was the spectral song of polycyclic aromatic hydrocarbons, or PETs. These are not simple molecules. They are elaborate interlocking rings of carbon and hydrogen, the stuff of soot and smoke, the organic grit found in the tail of a comet, or in the billowing clouds of a stellar nursery here in our own Milky Way. They are the precursors to tar to asphalt, and some cosmochemists believe to the very building blocks of life itself. We find them everywhere in the modern universe, a ubiquitous sign of cosmic life, death and recycling. But finding them, there in a galaxy so young it was barely a toddler, was like discovering a Shakespearean sonnet written in a caveman's scratches. It was a profound, almost offensive violation of the cosmic timeline. The first reaction within the inner circles of the JWST science teams was not excitement. It was a cold, professional certainty of error. The universe we had so carefully modelled for decades simply did not allow for this. In that primordial furnace just a few 100 million years after the Big Bang, the cosmos was supposed to be chemically simple. A vast ethereal ocean of hydrogen and helium, seasoned with only the lightest dusting of heavier elements forged in the first titanic stars. The universe hadn't had the time. It hadn't had the generations of stars living and dying, seeding the void, with the carbon necessary to build these molecular lattices. To create a pH, you need a specific environment, the carbon-rich, relatively gentle outflows of aging dying stars like our own sun, or the violent chaotic aftermath of a supernova. These processes take time, hundreds of millions, even billions of a year to build up a detectable reservoir. The signal had to be a mistake. And so began an inquisition, a rigorous, merciless interrogation of the data, the telescope and the scientists themselves. The first suspect was always the instrument. Could JWST's own revolutionary sensitivity be its undoing? Perhaps some subtle vibration in the mid-infrared instrument MIRI was creating a false resonance. Teams were tasked with recalibrating everything, running endless diagnostic tests, scrutinizing the behavior of every single pixel on the detector array. They scoured the engineering telemetry, searching for a temperature fluctuation, a voltage spike, a microscopic flaw that could masquerade as a molecule at the edge of space-time. They found nothing. The telescope was performing with chilling, flawless precision. The ghost in the machine was not in the machine itself. The next suspect was the light's long journey to us. Could this signal be a contaminant? A chemical mirage created by some intervening cloud of gas much closer to home? Was it possible that an unassuming, uncatalogued galaxy, billions of light-years in front of their ancient target, was imprinting its own mature chemistry onto the pristine light from the dawn of time? This was a more plausible, more comforting explanation. It would mean the discovery was a bust, but it would also mean our understanding of the universe remained intact. Astronomers began a painstaking process of cosmic forensics. Using other instruments on the ground and in space, they built a three-dimensional map of everything that lay between Earth and that distant galaxy. They searched for the telltale signs of a foreground imposter, a gravitational lensing anomaly, anything that could corrupt the signal. The path was clear. The light's journey had been uninterrupted. The signature was unequivocally coming from its source, from that nascent island of stars burning in the cosmic morning. With the hardware and the environment absolved, the investigators turned their suspicions inward to their own software and methods. The raw data from a telescope like Webb isn't a simple photograph. It's a torrent of information that has to be decoded, cleaned, and interpreted by complex algorithms. Perhaps somewhere in those millions of lines of code a subtle bias existed. A mathematical assumption that, when applied to the faint signals from the early universe, amplified noise into a phantom detection. Rival teams, using independently developed software pipelines, were brought in to process the raw data from scratch. It was a scientific bake-off at the highest level, a crucial check and balance against confirmation bias. Days turned into weeks of silent, furious computation, and when the results came back, the ghost was still there, unchanged, unflinching. Every independent analysis converged on the exact same impossible conclusion. The moment of truth could no longer be delayed. The team had to target another galaxy from that same primordial epoch. If this was a singular fluke, a 1 in a trillion statistical anomaly, it would not appear again. But if it was real, if it was a fundamental property of the early cosmos, then the signature would be waiting for them. The request was submitted. The world's most powerful time machine swiveled its golden gaze across the void, settling on a new, equally ancient target, a smudge of light named Sears as 93316. There was a palpable tension in the scientific community as they waited. This was no longer just about confirming a strange signal. It was about defending or dismantling a central pillar of modern cosmology. The new data streamed back to Earth. As the files downloaded and the algorithms went to work, a profound silence fell over the control rooms, and then it appeared on the screens. First as a flicker, then as a solid line. The same spectral song, the same intricate, unbelievable fingerprint of complex organic molecules. It was there. And then they pointed Webb to another primordial galaxy and another, and it was there again and again. This was not an anomaly. It was a chorus. The early universe, the one we had imagined as a simple barren place of gas and fire, was singing a symphony of carbon. The process of peer review, normally a staid academic exercise, became a crucible. The first draft of the paper, submitted to a prestigious journal, was met with what could only be described as profound institutional shock. The anonymous reviewers' leaders in their fields were merciless. They tore the analysis apart line by line, demanding more proof, more checks, more evidence to rule out every conceivable, however improbable source of error. They were not being obstructionist. They were being good scientists, acting as the immune system of human knowledge, attacking a foreign concept that threatened the health of the entire organism. The back and forth was intense, a volley of questions and rebuttals that pushed the team to the absolute limits of their abilities. They reran simulations, developed new statistical tests, and refined their arguments until their case was no longer just compelling, but an ironclad, irrefutable truth. When the paper was finally accepted and published, the news didn't just make ripples, It triggered a seismic shockwave. For decades, the story of cosmic evolution had been a grand, sweeping and linear narrative. It began with the simple elements forged in the Big Bang's heart. These elements formed the first stars. These stars, through their nuclear alchemy, created heavier elements like carbon and oxygen. They lived, they died, and in their explosive death throes they scattered these new ingredients into the cosmos. Over billions of years, this process repeated a slow, generational enrichment that gradually made the universe a more complex and interesting place. It was a patient, elegant story, and it was in a fundamental way wrong. The discovery of abundant, complex organic molecules in the universe's first act shredded that timeline. It presented a universe that was seemingly born with a startling degree of chemical maturity. It was like watching a recording of a new solar system's formation, and seeing in the swirling protoplanetary disk not just dust and gas, but fully formed continents and oceans. The foundational assumptions that had underpinned countless theories about the pace of star formation, the efficiency of chemical enrichment, the conditions for planet formation were now all thrown into question. The carefully constructed edifice of cosmic history had developed a crack right down its centre. We had spent years, decades asking the question, is this signal real? We had hounded it, tested it, and tried to kill it, but it had survived every attempt. Its reality was now undeniable. And in the silent acceptance of that fact, a new, far more profound and unsettling question began to take shape, echoing in the halls of universities and research institutes around the world. The central mystery of the cosmos had shifted on its axis. We were no longer staring at a ghost in the data, wondering if our eyes were deceiving us. We were staring at the ghost's very real footprint imprinted in the clay of creation itself, and we were forced to ask a question that struck at the very heart of our own existence. How? How could the universe build something so complex so quickly? Where were the chemical factories operating with such impossible, unheard-of efficiency? The stellar forges we knew about were too slow, the known pathways of synthesis too ponderous to explain this premature burst of organic creativity. It implied a hidden chapter in the cosmic story, a secret and accelerated youth that we had never even conceived of. Were the first stars fundamentally different from the stars we see today, behaving in ways our models failed to predict? Were they celestial blowtorches of unimaginable power, living fast, dying young, and seeding their galaxies with carbon at a furious pace? Or was there another, more exotic mechanism at play? A form of chemistry, perhaps, that operates in the cold, dark dust clouds between the stars. A patient, unseen assembly line for life's precursors working far faster than we ever thought possible. The implications were staggering. If the raw ingredients for life, these complex carbon-based molecules, were not a late-stage, rare byproduct of cosmic evolution, but a common early feature of it, what did that mean for the probability of life elsewhere? It suggested that the primordial ooze wasn't confined to the warm little ponds of nascent planets, but that the entire cosmos from its earliest moments was awash in it. The game had changed. We had arrived breathless at a new frontier, not of space, but of time. The question was no longer what the early universe was made of. The question was how it had put the pieces together so fast, building a universe, seemingly eager from its very first breath to become a home. And so the confirmation arrives not with a gentle whisper, but as a seismic shockwave propagating through the very foundations of cosmology. The light from that impossibly distant galaxy carried with it a signature we were told should not exist, a spectral fingerprint of complexity that throws our entire cosmic timeline into disarray. This isn't just about finding a stray molecule in an unexpected place. It's about pulling a single critical thread from the grand tapestry we have so carefully woven to tell the story of our universe. Now as we watch, the whole magnificent fabric begins to unravel. The first domino to fall is the one we thought most secure our understanding of the cosmic production schedule. Complex molecules, these polycyclic aromatic hydrocarbons, are built from carbon. And carbon, like all elements heavier than helium, is stellar ash. It must be forged in the nuclear furnaces of stars and then cast out into the void through the violent throes of their death. Our models, painstakingly calibrated against observations of the nearby universe, insisted this was a slow generational process. It required the birth life and explosive death of one generation of stars simply to seed the interstellar clouds, with enough raw material for the next generation to incorporate. Think of it as a cosmic ecosystem, where the death of the old provides the nutrients for the new. This cycle, we believe, took time hundreds of millions, if not billions of years to build up any significant chemical richness. But JWST has shown us a universe barely 500 million years from its inception already rich with the very molecules that should have taken eons to appear. The implication is staggering. It means the first stars, the behemoths we call Population 3, were not just pioneers, they were hyper-efficient industrial forges. These hypothesized titans, composed of nothing but pure hydrogen and helium, must have roared to life, burned through their fuel at an almost unimaginable rate, and then detonated in cataclysmic supernovae of a scale we can barely model. They lived fast and died young, but their deaths were profoundly generous, bequeathing to the infant cosmos a vast inheritance of heavy elements. The universe didn't gently accumulate complexity. It seems it was kick-started with a burst of alchemical violence polluting its own pristine cradle almost from the moment the lights turned on. The quiet, contemplative dawn we had envisioned is being replaced by the clangor of a celestial factory working in frantic overtime. This frantic production of heavy elements creates another more immediate consequence, solving one cosmic puzzle while deepening the mystery of another. For galaxies to form, for stars to be born, a fundamental battle must be won. It is the eternal war between gravity, which seeks to pull vast clouds of gas together, and thermal pressure, the outward push of heat that resists collapse. In the primordial universe with only hydrogen and helium, gas clouds were inefficient radiators. They held on to their heat stubbornly, making it extraordinarily difficult for gravity to gain the upper hand and trigger the birth of stars. It was like trying to build a sandcastle with dry shifting sand. But heavy elements, and especially the dusty carbon-based molecules JWST has found, are a game-changer. They act as a cosmic refrigerant. These complex structures are incredibly effective at absorbing ambient heat and then radiating it away into the coldness of space as infrared light. With this cooling mechanism in place, the thermal pressure within a gas cloud plummets. Gravity's victory becomes swift, decisive, and spectacular. The cloud collapses, it fragments, and it ignites into a frenzy of starbirth. What we are seeing is not just the product, but the process itself. These impossible molecules are not merely a surprising discovery. They may be the very engine that drove the impossibly rapid evolution of the early universe. They are both the evidence of early star formation and the catalyst that made it possible, a self-perpetuating cycle of creation that spun up far faster than we ever dared to believe. This accelerated timeline doesn't just affect individual stars, it forces a complete rewrite of the architectural blueprints for the largest structures in the cosmos, the galaxies themselves. For decades, the dominant theory has been one of hierarchical formation. It's an elegant bottom-up story. In this model, the first objects to form were small dwarf proto-galaxies. Over billions of years, these modest collections of stars would slowly dance together, pulled by the invisible hand of dark matter, colliding and merging in a majestic and protracted process of cosmic construction. A galaxy like our Milky Way in this view is a modern metropolis built upon the foundations of countless ancient villages that have been assimilated over time. It's a patient, stately and gradual evolution. JWST's discoveries, however, paint a very different picture. We are now seeing large, well-structured and chemically mature galaxies at a time when only the most primitive galactic hamlets should exist. The presence of these complex molecules provides the critical physical explanation for how this could happen. If gas clouds can cool with extreme efficiency, they can collapse much more violently and on a much grander scale. Instead of forming a scattering of small dwarf galaxies, it becomes possible for vast turbulent reservoirs of gas to undergo a monolithic collapse, igniting into a single massive starburst that forms the core of a great galaxy in a fraction of the time. It's the difference between building a city brick by brick over centuries and having the entire downtown skyline rise out of the ground in a single breathtaking decade. This doesn't mean mergers didn't happen, but it suggests that galaxies could grow enormous and sophisticated on their own, far earlier than the old models allowed. The cosmic city planners, it seems, were working from a much more aggressive schedule. The reverberations of this discovery continue to spread shaking, Yet another pillar of modern cosmology, the story of rhyonisation. After the initial fires of the Big Bang cooled, the universe was plunged into darkness. For hundreds of millions of years it was filled with a thick neutral fog of hydrogen gas that made it opaque to light. This was the cosmic dark ages. The end of this era was heralded by the light of the very first stars and galaxies whose intense ultraviolet radiation acted like a celestial blowtorch burning through the fog. This process, known as the Epoch of Rhyonisation, transformed the universe from a murky neutral soup into the transparent ionized cosmos we see today. But a fierce debate has long raged among astronomers. What exactly provided the power for this great transformation? Was it a tiny swarm of countless faint dwarf galaxies, each contributing its small flame, or was it a few much larger, more brilliant galactic beacons that did the heavy lifting? The timing, the duration, and the very nature of reionization depended on the answer to this question. Now the discovery of hyper-efficient star formation in large early galaxies provides a powerful new candidate for the source of this cosmic dawn. It suggests that these early chemically enriched galaxies were not faint flickers, but brilliant searchlights blasting out torrents of ionizing photons. This could mean that rhyonisation happened faster, perhaps more violently, and in a more patchy, uneven way than our smoother models predicted. Imagine not a gentle global sunrise, but a dramatic celestial thunderstorm with blinding flashes of light erupting from isolated pockets of intense activity, their ionization bubbles expanding outwards until they finally overlapped, burning away the last shadows of the cosmic dark. And here in the final, most profound ripple effect, the story turns towards us. It turns towards the question of origins of planets and of life. The story of our own solar system is a story of dust and gas. The sun formed and the leftovers, a swirling protoplanetary disk rich in heavy elements like carbon, oxygen, silicon and iron, became the building blocks of the planets. These elements, this cosmic dust, are the non-negotiable requirement for rocky worlds. Without them, there is nothing from which to build a home. Our timeline told us that the universe had to age for billions of years before it was sufficiently seasoned with these materials. We believed that the first generations of stars had to live and die, and then their successors had to live and die, each generation adding its contribution to the cosmic inventory of elements. Only then, in a mature, chemically complex universe, could a solar system like ours finally be assembled. The first Earth-like worlds, we concluded, couldn't have formed until the universe was at least 3, 4, or even 5 billion years old. But the evidence for complex carbon chemistry, just a few 100 million years after the Big Bang, demolishes that comfortable assumption. If the dust and heavy elements were already there, what does that truly mean? It opens a door to a possibility so profound it is almost heretical. It suggests that the raw materials for rocky planets could have been available billions of years earlier than we ever thought possible. The first cradles for worlds might have been assembled not in the universe's adulthood, but in its infancy. This does not mean that life existed then. The conditions in these early violent galaxies would have been incredibly hostile, blasted by radiation from monstrous stars and bombarded by frequent supernovae. But it forces us to ask a new question. Not when did life become possible, but when did the ingredients for worlds like ours first appear on the cosmic stage? The answer whispered to us by JWST across 13 billion years of expanding space is that the stage was set almost as soon as the curtain was raised. The potential for planets, the very bedrock of biology, may be a far more ancient feature of our universe than we ever had the courage to imagine. We stand therefore in the rubble of our own elegant theories. The discovery of a single type of molecule has triggered a cascade failure in our understanding of nearly every fundamental process in the early cosmos. The serene, gradual and orderly evolution we had mapped out is being replaced by a vision of a universe that was far more chaotic, far more dynamic, and astonishingly precocious. It was a universe in a hurry, building its greatest structures and seeding its future worlds with a ferocity that defies all our previous expectations. We are now like cartographers who have discovered that the continent we thought we knew is shaped completely differently, its mountains higher, its rivers flowing faster, its very existence owing to forces we had failed to consider. The old maps are now useless. The neat, tidy story of our cosmos has been torn apart, and in its place is a thrilling, intimidating, and irresistible mystery. If our models are broken, if our timeline is wrong, then how do we even begin to build a new story that fits the facts? What new physics, what new understanding of the dawn of everything must we now uncover to make sense of this impossible, beautiful reality? And so the gauntlet was thrown down, not by a rival, but by the universe itself. The presence of these complex carbon-based molecules, these polycyclic aromatic hydrocarbons, in a cosmos barely 700 million years old, presented a stark and beautiful contradiction. The raw materials, the heavy elements forged in the hearts of stars, were simply not supposed to exist in such abundance. The time needed to build these intricate molecular structures, let alone the calm, stable environments required for their assembly, was a luxury the infant universe did not possess. It was a chaotic, violent, radiation-scorched wilderness. Yet here was the evidence etched in faint spectra of light from across 13 billion years of cosmic history. This was not a flaw in the data. This was a fundamental flaw in our understanding. In laboratories and universities across the planet, a silent, urgent scramble began a race to solve an impossible chemistry problem posed by the cosmos itself. The old models were broken. It was time to build new ones. The first and most audacious of these new ideas begins not with chemistry, but with cataclysm. It returns us to the very first generation of stars, those mythological titans known as population 3 stars. We have long imagined their deaths as the universe's inaugural firework display, the first supernovae to seed the void with elements heavier than hydrogen and helium. But what if our imagination was too tame? What if these were not just supernovae, but something far more potent, something that astronomers now call hypernovae? Imagine a star not of 10 or 20, but of hundreds of solar masses, a blue-white behemoth of pure primordial gas burning with an intensity that beggars belief. When a star of such colossal energy collapses, it does not simply explode. It detonates with a fury that can outshine its entire host galaxy. This is not a stellar death. It is a cosmic re-engineering event. The established models of stellar evolution suggested a slow-layered process. Inside a dying star, heavier elements form in concentric shells like a cosmic onion. An iron core is surrounded by silicon, then magnesium, oxygen, carbon, and so on. When the star explodes, these layers are blasted outwards. But the process was thought to be inefficient, with much of the newly forged material falling back into the collapsing core to become a black hole or neutron star. Crucially, the mixing of these layers was believed to be limited. You wouldn't get a perfect homogeneous blend of elements hurled into space. This tidy layered explosion simply could not deliver the right mixture of carbon, oxygen, and other heavy elements fast enough and far enough to explain what JWST had seen. The early universe would be left with isolated pockets of enrichment, not the widespread chemical complexity we were now observing. The new hypernova models, however, paint a far more violent and, paradoxically, a more creative picture. The collapse of a truly massive star can be asymmetric and wildly unstable. The resulting explosion is not a neat spherical shockwave. Instead, it fires off titanic focused jets of matter, travelling at nearly the speed of light. These jets, powered by the immense gravitational energy of the collapsing core and its rapidly spinning magnetic field, act like cosmic drills. They bore through the star's own outer layers at unimaginable speeds, violently churning and mixing the pristine unburnt hydrogen and helium on the outside with the freshly synthesized carbon, oxygen, and silicon from the deepest parts of the stellar furnace. This is the crucial difference. It's not a layered ejection. It's a high-velocity, perfectly blended cosmic cocktail. In this scenario, the hypernova isn't just a bomb, it's a galactic blacksmith with a power hammer. It doesn't just create the raw materials, it processes and distributes them with astonishing efficiency. The jets punch through the star and scream out into the surrounding interstellar medium, carrying a rich cargo of heavy elements, far beyond the immediate vicinity of the explosion. They act like a high-pressure spray gun, coating vast regions of the primordial galaxy with the building blocks of molecules. A single one of these events could enrich a volume of space thousands of light years across seeding countless nascent star-forming clouds with the carbon necessary for life's precursors. This mechanism short-circuits the long, slow timeline we had always assumed was necessary. It bypasses the need for multiple generations of stars to gradually build up the universe's inventory of heavy elements. With hypernovae, the cosmos gets a chemical jumpstart. A handful of these primordial titans dying in a blaze of glory could instantly create the carbon-rich environments that JWST has now revealed. The impossible molecules are no longer impossible if their constituent atoms were delivered express pre-mixed and ready for assembly by the most powerful explosions the universe has ever known. It is a compelling, elegant, and terrifyingly beautiful solution. But forging the atoms is only the first half of the puzzle. How do you then assemble them into the complex interlocking rings of a polycyclic aromatic hydrocarbon? Here we confront the second great demon of the early universe, radiation. The very same giant young stars that die as hypernovae are during their lifetimes celestial blowtorches. They flood their surroundings with torrents of high-energy ultraviolet radiation, a sterilizing bath of photons powerful enough to shatter any delicate chemical bond that might dare to form. For decades we believed this environment was the enemy of chemistry, a cosmic desert where complex molecules could not survive, let alone be constructed. The energy was simply too high, the environment too hostile. It would be like trying to build a house of cards in the middle of a hurricane. Yet a new and radical school of thought is emerging, one that proposes a stunning paradox. What if this destructive force could, under the right conditions, become a creative one? What if the intense radiation wasn't the problem, but part of the solution? This idea revolves around entirely new pathways for chemical reactions, pathways that are impossible in the calmer, cooler regions of our modern universe, but which might have been commonplace in the cosmic dawn. In this model, the relentless flood of ultraviolet photons is not a wrecking ball, but a form of radiation-driven alchemy. When a high-energy photon strikes a simple atom, or a small two-atom molecule, it doesn't just risk breaking it apart. It can also kick it into a highly energized or excited state. An atom in an excited state is fundamentally different. It's unstable, reactive, and desperate to shed its excess energy by forming new bonds. Imagine a cosmic dance floor where atoms are normally shy and reluctant to pair up. The intense radiation field is like a powerful driving music that forces everyone onto the floor. Suddenly, atoms that would never interact are energized, vibrating with potential, and far more likely to collide and stick together. Carbon atoms, ionized by the UV light, could become extraordinarily reactive, actively seeking out hydrogen to form the fundamental building blocks of organic chemistry. The radiation field, once seen as a purely destructive force, could actually be powering a high-energy production line. It could be driving chemical reactions at a blistering pace, forcing the assembly of simple hydrocarbons like methane and acetylene. These, in turn bombarded by yet more radiation, could be fused together into the stable, resilient ring structures of the PAHs. The very stability of these molecules, their interlocking hexagonal shapes, makes them uniquely capable of surviving the harsh UV environment once formed. They are the chemical diamonds forged under the immense pressure of the early universe's radiation fields. This theory transforms our entire perception of a stellar nursery. It is no longer just a place where stars are born. It is a crucible, a high-energy chemical reactor, where the very radiation from infant stars provides the catalyst for cosmic complexity. The destructive and creative forces of the universe are not in opposition here. They are one and the same, locked in an intricate, violent, and ultimately productive dance. It is a stunning reversal of scientific intuition, a testament to the universe's ability to find creative solutions in the most extreme conditions imaginable. The hurricane, it turns out, might be precisely how you build the house of cards, provided the cards themselves are forged in the storm. This idea is still in its infancy, with chemists and astrophysicists running complex simulations to see if these radiation-driven pathways are truly efficient enough to explain the sheer quantity of molecules that JWST has found. But it has opened a door to a new and exhilarating possibility that the birth of complexity was not a gentle, peaceful process, but a direct consequence of the universe's most violent and energetic youth. While the grand explosive theories of hypernovae and the subtle paradox of radiation chemistry capture the imagination a third, quieter revolution is taking place. This idea focuses on something we have long known existed, but may have profoundly underestimated: cosmic dust. For years, we viewed dust as little more than a nuisance, a celestial fog that obscured our view of distant stars and galaxies. We knew it played a role in star formation, but in the primordial universe we assumed it was scarce and insignificant. After all, dust itself is made of heavy elements like silicon, carbon, and oxygen. You need stars to die first to even make the dust. How could it be important when there had been so little time to create it? JWST's observations have forced a complete re-evaluation of this assumption. We now see that the early universe was surprisingly dusty, far more so than our models predicted. And this realization has unlocked a powerful new mechanism for building molecules. This theory presents dust grains as the unsung heroes of cosmic chemistry. Think of them not as fog, but as microscopic construction sites, sheltered harbours in the raging storm of the early cosmos. Each tiny grain, perhaps only a few millionths of a metre across, offers two things that are in desperately short supply: in the empty vacuum of space, a surface and a shield. The surface is critical. In the diffuse gas clouds of a young galaxy, individual atoms are few and far between. The chances of two specific atoms, say a carbon, and an oxygen meeting at the right time and with the right energy to form a bond are astronomically low. But a dust grain acts as a cosmic meeting point, a gravitational and electrostatic anchor. Atoms and simple molecules drifting through space can stick to its surface, a process called adsorption. Suddenly they are no longer lost in the void. They are neighbours held in close proximity on the grain surface. This dramatically increases the likelihood of them reacting. The dust grain becomes a tiny chemical factory concentrating the raw ingredients and holding them still long enough for chemistry to occur. But its role is even more profound. The surface of the grain itself can act as a catalyst, an intermediary that facilitates reactions without being consumed. It can absorb the excess energy released when a new bond forms, preventing the newborn molecule from immediately shattering apart. It provides a stable, protected workbench where simple molecules can be assembled piece by piece into more complex structures. Simple hydrocarbons could form on the surface, and then over time link up to create the elegant multi-ringed PAH that JWST has detected. The grain is not just a passive meeting place, it is an active participant in the creative process. It is the celestial enzyme that makes impossible chemistry possible. And then there is its role as a shield. Even a minuscule grain of dust can provide a safe haven from the destructive ultraviolet radiation pouring from young stars. Molecules forming on the side of a grain facing away from a bright star or in a protected shadow, a microscopic oasis where they have the time they need to assemble and stabilize. Once formed, these hardy patch molecules can be ejected from the grain surface, back into the gas cloud, perhaps dislodged by the energy of another photon strike or a gentle warming of the grain. Now, robust enough to survive on their own, they populate the interstellar medium, creating the spectral signatures that JWST would one day detect 13 billion years later. This theory provides a tangible physical mechanism that works in concert with the other ideas. The hypernovae forge and distribute the raw elements. The dust grains made from those very elements then become the factories that use those elements to build the molecules. It's a complete self-consistent ecosystem for cosmic creation. It suggests that from the very beginning the universe was not just making stars, it was simultaneously building the workshops needed to construct the chemistry of life. Ultimately, it may be that there is no single silver bullet explanation. Science rarely offers such simple narrative comfort. The truth, as is so often the case in the cosmos, is likely a grander synthesis, a story woven from all these threads. We are likely looking at a complex interconnected process, a symphony of creation, with many instruments playing in concert. Imagine the scene in a young star-forming galaxy. A colossal population 3 star detonates as a hypernova, its jets blasting a turbulent pre-enriched mixture of carbon and silicon into a vast cloud of hydrogen gas. This violent act both delivers the ingredients and triggers a new wave of star formation within the cloud. As these new stars ignite, they flood their surroundings with intense ultraviolet light. In the diffuse gas between the stars, this radiation field drives high-energy chemical reactions, fusing atoms into simple molecules in a fiery crucible. Simultaneously, within the denser, colder clumps of the cloud, the newly formed dust grains forged from the hypernova's ashes begin their quiet work. They act as shielded assembly platforms, gathering atoms on their surfaces and catalytically building them into complex pairs, protecting them from the very radiation that is driving chemistry elsewhere. It becomes a dynamic multi-environment system. One process dominates in the hot irradiated regions, another in the cold shielded ones. Molecules formed on dust grains are then released, enriching the gas, which is then processed further by the radiation fields. It is a breathtakingly complex and beautiful picture of cosmic ecology, where violence and sanctuary destruction and creation all work in a delicate, powerful balance. This is how the textbooks are being rewritten. Not with a single new sentence, but with entire new chapters dedicated to processes we're only just beginning to comprehend. The James Webb Space Telescope has not just shown us a picture of the early universe, it has forced us to rethink the fundamental physics and chemistry that governed it. It has revealed a cosmos far more capable, far more efficient, and far more eager to create complexity than we ever dared to imagine. The impossible molecules are a message from our own cosmic past, a testament to the universe's relentless ingenuity. They tell us that the journey from the Big Bang to biochemistry may have had crucial, unexpected shortcuts. And as we stand here deciphering these new cosmic blueprints, we realize that the quest is no longer just about finding out what the early universe looked like. It is about understanding the very processes that allowed a universe like ours to exist at all and to ultimately give rise to us. The climax of this discovery is not an answer, but a doorway to a whole new realm of questions, and so the impossible has become the undeniable. The chemical ghosts we pursued through the deepest corridors of time have finally materialized not as faint apparitions, but as vibrant, complex structures painting the dawn of creation in colors we never knew existed. The journey we have taken together from the quiet confidence of old theories to the dizzying precipice of this new reality has been nothing short of a revolution. We began in a familiar cosmos, one we thought we understood, a universe born in fire, yes, but then cooled into a state of profound simplicity. For eons, our models painted a picture of a nascent cosmos composed almost exclusively of hydrogen and helium, a placid chemical ocean waiting patiently for the first stars to begin the slow, arduous work of forging heavier elements. It was a narrative of gradualism, of cosmic patience, where complexity was a recent innovation, a luxury afforded only to galaxies that had lived and died for billions of years. We believed the universe had to learn the alphabet of the elements before it could ever hope to write the poetry of organic molecules. Through the golden eye of the Webb telescope, we have now read that poetry etched into the light of galaxies born when the cosmos was but a toddler barely a few 100 million years old. Every spectral line we have dissected in our journey, every unexpected absorption feature that defied easy explanation, was a word in a language we are only now beginning to comprehend. The carbonaceous dust grains, those microscopic specks of soot we once thought were the products of a mature, well-developed universe, were there. They were there almost from the beginning, acting as cosmic construction sites, miniature catalytic converters where atoms could meet, mingle and bond in the cold vacuum of space. The polycyclic aromatic hydrocarbons, those complex ringed molecules we associate with star-forming nurseries, and the interstellar medium of our own Milky Way were not a modern invention. They were ancient architects, their intricate molecular scaffolding already present in the universe's earliest building blocks, shaping the light and the destiny of the very first galaxies. This discovery does more than just add a new chapter to our cosmic history. It forces us to tear out the opening pages and begin again. The timeline we held as a near-sacred text, the orderly progression from simple to complex, has been completely shattered. Imagine building a cathedral not by laying a foundation and slowly raising the walls brick by brick over centuries, but by discovering that the ornate stained glass windows and the complex vaulted ceilings were somehow present from the moment the very first stone was laid. This is the magnitude of the paradigm shift we are now facing. These complex molecules were not merely passive byproducts of the first stellar generations, the exhaust fumes of creation. They were active agents. They were participants. Their very presence in those primordial clouds of gas had a profound and immediate impact on the evolution of the cosmos. In the cold, diffuse gas of the early universe, These molecules acted as phenomenally efficient radiators, as celestial cooling fins that could bleed heat away into space. Hydrogen atoms alone are clumsy and inefficient at this task, but these large vibrating, rotating organic structures could absorb the kinetic energy of the gas, its heat, and radiate it away as infrared light, the very light the Webb telescope is so exquisitely designed to see. This cooling process is not a trivial detail. It is the master switch for star formation. By chilling the hearts of these vast gas clouds, the molecules allowed gravity to win its eternal battle against pressure far more easily and far, far sooner. They enabled the clouds to collapse under their own weight, to fragment and to ignite into the brilliant fires of the first stars at a rate and an efficiency our previous models deemed impossible. The universe, it turns out, was not a slow, methodical builder. It was a bootstrapped, self-accelerating system. The first massive, short-lived stars forged the first heavy elements in their cores and then violently seeded their surroundings with them in supernova blasts. Almost instantaneously, these elements, this carbon, this oxygen, found themselves in a cosmic crucible forming dust and complex molecules. Those molecules then acted as a turbocharger for the next generation of stars, cooling the gas to create denser, more fertile stellar nurseries. More stars meant more elements, which in turn meant more complex molecules, and so on in a powerful feedback loop that kick-started cosmic evolution. The impossible molecules were the very engine of cosmic dawn, hastening the formation of stars, accelerating the enrichment of galaxies, and fundamentally changing the texture and structure of the early cosmos. The universe did not wait to become complex. It used complexity to build itself. We have arrived at a new shore of understanding, but the continent that stretches out before us remains almost entirely unexplored. Every answered question, it seems, has given birth to a dozen more, each one more profound than the last. Webb has shown us that these molecules exist, but now we must ask, how widespread are they? Was the galaxy SPT 041847, with its startling chemical richness, a bizarre anomaly, a cosmic outlier? Or is it the standard blueprint for galactic infancy? Are these complex organics a universal feature of the dawn of time present in every single proto-galaxy, struggling to be born in that early violent era? To answer this, astronomers will now pivot, dedicating hundreds, even thousands of hours of the telescope's precious time to stare deeply into a wider array of the universe's first galaxies. They will conduct a grand cosmic census, moving from the discovery of one to a statistical understanding of the many, mapping the prevalence and distribution of these life-giving ingredients across the full tapestry of the early universe. And what of their specific origins? We see the final product, the molecular smoke, but we have yet to fully understand the chemical fire that forged it. What are the precise chemical pathways, the detailed reaction networks, that could build such intricate structures so rapidly in the harsh, radiation-drenched environment of the first galaxies? Was it the surfaces of those newly formed dust grains that served as the key, providing a solid-state sanctuary where atoms could hold hands? Or were there exotic high-energy gas phase reactions driven by the intense ultraviolet glare of the first stars that we have yet to account for in our models? Unravelling these chemical mysteries will require a new synergy between observational astronomers and laboratory astrochemists here on Earth. Scientists will work to replicate the extreme conditions of the early universe in vacuum chambers, bombarding icy mixtures with radiation, trying to recreate the specific molecular signatures that Webb has uncovered. It is a form of cosmic archaeology, using terrestrial experiments to decipher the molecular fossils buried in the light from 13 billion years ago. The next great frontier for the telescope will be to push beyond detection and into the realm of characterization. Can we use its powerful spectrographs to find even more complex molecules, to move beyond the general class of precarious and identify specific species? Could we find the spectral fingerprints of even larger, more lifelike structures? Perhaps amino acids. The simplest, like glycine, have been found in meteorites and in molecular clouds within our own galaxy. To find their signature in the dawn of time would be a discovery that would reverberate through all of science, a sign that the fundamental building blocks of proteins were not a late-game invention of planetary biology, but were instead forged in the maelstrom of the universe's birth. This is the breathtaking territory that Webb is now opening for us. It is no longer a question of if organic chemistry exists in the early cosmos, but a question of how far it goes. We are standing at the threshold, peering into a chemical wonderland that we are just beginning to map, and every new observation promises another piece of this grand cosmic puzzle. Webb is not just a telescope, it is our generational opportunity to witness the universe's chemical coming-of-age story, to watch for the first time as the cosmos assembled the very toolkit of life. For embedded within these spectral lines, within these faint signals from across an ocean of time and space, lies the most profound implication of all. It touches upon the deepest question we have ever dared to ask ourselves. Are we alone? This discovery does not, of course, provide the answer. We have not found life. We have not found biology. But what we have found is perhaps just as momentous. We have found that the conditions for life, the raw materials, the fundamental chemical ingredients that we are made of, are not a rare or recent cosmic development. They are ancient. They are primordial. They are woven into the very fabric of the cosmos from its earliest moments. The timeline for a potentially habitable universe has just been rewound by billions and billions of years. The idea of a sterile, barren early cosmos hostile to the chemistry of life has been replaced by the vision of a universe that was in a very real sense born pregnant with possibility. Think of what this means. If the carbon, the complex organics, the very stuff of planets and people, was already abundant in the first billion years, then the opportunity for life to arise was not limited to a few quiet corners of the modern universe. The seeds of biology may have been sown in the soil of the very first Earth-like planets to ever form orbiting stars in galaxies that are now long dead, and gone, their light only just reaching us now as faint red-shifted echoes. We have always tended to view ourselves, our solar system, our galaxy, as the centre of the story, assuming that the conditions that led to us were the product of a long, slow maturation. But perhaps we are not the first chapter. Perhaps we're just one verse in a cosmic epic that began almost as soon as the universe itself had cooled enough to allow it. The universe, it seems, has been practicing the chemistry of life for almost its entire 13.8 billion-year history. This realization changes everything. It transforms the night sky from a vast empty museum of physical forces into a sprawling dynamic chemical laboratory. It means that every distant galaxy Webb shows us, no matter how ancient, is not just a collection of stars and gas, but a potential cradle, a place where the same molecular journey that unfolded on our world could have also begun. The organic molecules in your body, the carbon atoms that form your DNA, the complex structures that allow you to think, to feel, to wonder their story did not begin on a warm little pond on a young Earth. Their story began in the hearts of those first furious stars. It began in the shock waves of the first supernovae. It began in the cold, dark clouds of the infant universe where those impossible molecules first coalesced against all odds, their existence a quiet promise of the richness that was to come. We are the direct descendants of that ancient chemistry. We look out into the cosmic dawn, and we see the faint spectral reflection of our own molecular origins. The Webb Space Telescope has given us a new creation story, one written not in myth or scripture, but in the universal language of light and matter. It is a story of a universe that was never simple, never empty, but was instead biased towards complexity, saturated with the potential for life from its very first moments. Our quest for understanding will of course continue. New telescopes will be built, new questions will be asked, and new generations will push the boundaries of our knowledge even further. But we will forever be the generation that first witnessed this, the generation that looked back to the beginning and discovered that the universe was not waiting for us to arrive. It was preparing for us all along,